of enolate formation. Okay? And so I'm going to draw a ketone. Specifically, I'm going to draw a methyl ketone where I'm only showing one of the hydrogens off that methyl ketone. Okay? You should have learned that the pKa value for this is approximately 20. Okay? And what I want to look at is the effect of base on this equilibrium. Okay? So we're going to consider equilibrium, so I'm going to use my equilibrium arrow. And obviously, if I have a base, my most acidic hydrogen on the ketone is the alpha carbon. So specifically, I'm going to extract this proton with this base to generate an enolate anion. Okay? And of course, I get Hb plus. Okay? Now, one of the things you should have learned is that this equilibrium is affected by the strength of the base, right? One of the things I teach when I teach the first semester course is this simple rule that is strong acid, strong base always leads to the weaker acid base pair. And so one of the things I want to share with you before I get you guys the data is, in general, stronger bases drive the equilibrium to the right. And I'm going to abbreviate equilibrium with EQ. Okay? And the reason for this is equilibrium favors the side with the weaker acid. Okay? So you should have seen both these concepts and have seen that in the past. Again, strong acid, strong base always goes to the weaker acid, right? So if you think about both of these, of course, if I have a stronger base, it's going to pluck off this proton and drive that equilibrium. And of course, equilibrium will favor the side with the weaker acids. So one of the things I'm going to look at is I need to find a very strong base that has a weak conjugate acid, okay? So I'm going to create a little table for you guys. And I'm going to list conjugate bases. So we're going to look at sodium hydroxide, its conjugate acid is water. I'm going to look at sodium ethoxide, its conjugate base is ethanol. I'm going to look at potassium t-butoxide, its conjugate base is tertiary butanol. And finally, two more. I'm going to look at sodium hydride, its conjugate base, its conjugate acid is hydrogen gas, okay? And then I know Dr. Schwann talked a little bit about aldehyde. I'm going to abbreviate aldehyde in this fashion, and then I'll write its structure down in a moment.
Dr. Martinez, can you move the paper up a little, please?
Yes, I will.
Thank you.
Okay. And the conjugate acid for this is the secondary amine. I'm going to draw the structure here, so that's what aldehyde is. The conjugate base of aldehyde is diisopropylamine. Okay. Now we want to look at the pKa for these Hb plus. Okay. So if I does that light help? So water obviously is 15.7. This is approximately 16. This is 18. Hydrogen gas has a pH value of 35. And LDA, depending on what book you use, it can range from 38 to 40. Let's settle at 40. Okay. Now, what I just did for you is I just listed a bunch of bases with the conjugate acid, and I listed the pKs for this conjugate acid. But again, what we want to use is specifically how these bases affect this equilibrium. So what I'm going to show now is how much enolate is formed using these bases for that reaction. It turns out if you use sodium hydroxide or sodium ethoxide, the amount of enolate formed is less than 1%. So in other words, with these two weak bases, the equilibrium is highly shifted to the left. Okay, so we don't have much. If I go to a slightly stronger base, such as tertiary T-betoxide, we only get 1 to 10%. It's still not very good. So 110% tells me if I want to settle at 10%, 90% of the equilibrium is the ketone. Okay, if I go to now the stronger bases, sodium hydride or LDA, what we find is that all the reaction goes to the far right and favors 100% enolate formation. So you can see right off the bat, depending on one base, I can either have an equilibrium or I can form the enolate exclusively. Okay, one thing I have to mention, in order to get 100% here, obviously I need excess base relative to the ketone. So if I have a little bit extra sodium hydride or LDA, I will get 100% of the ketone or whatever proton source I'm looking at going to 100% enolate formation. Now, as I promised, LDA is nothing other than diisopropyl-amide, lithium diisopropyl-amide. So I have a lithium here that has a positive, and I have a nitrogen with two sets of lone pair of electrons, which gives it a negative charge. Okay, this is an extremely strong base, but the other part of this is that it's sterically hindered. So since it's a strong base and sterically hindered, what do I mean by sterically hindered? Well, because of these large diisopropyl groups, this nitrogen is not nucleophilic. So we often say this is a strong non-nucleophilic base. And I'll move my hand so you can see that, okay? What I will do, and just in case you guys can't see certain things, I will scan these this afternoon and I'll pulse them, okay? Any questions up to this point? All right, so let me proceed with this type of discussion. Well, why is this important? Well, if I now go back to that reaction, and here I'm using acetone, now we can see that if I treat acetone with sodium hydroxide, I expect the equilibrium to be highly shifted to the left and not towards the enolate.
Professor?
Yeah.
Can you explain why it's not nucleophilic again, please?
Sure. Let me get to the next one. I'm going to draw it right now, and then I'll definitely go over that.
Okay, thank you.
Okay, value for the ketone is 20. The pK value for water is 15.7. I'm going to say 16. Okay. So recognize, if you consider this is the stronger acid, this is a weaker acid, so the equilibrium should be shifted towards reactants, not products. Now, in the case of aldehyde, okay, so let me redraw the structure of aldehyde. Aldehyde has two sets of lone pair of electrons, has a negative charge, and there's a lithium here, okay? This equilibrium is shifted all the way to the right because I form the enolate plus diisopropylamine. And again, diisopropylamine has a pKa value of approximately 40. Actually, it's 38, but we're going to say 40, okay, approximately. Okay. So you can see here, if you think about this, if you want to measure the equilibrium, you basically have the difference of power of 20, right? So since pKa values are logarithmic, the difference of 40 to 20 is 20. This basically, the reason it's shifted all the way to the right is we can roughly say that the equilibrium is k to the power of 10 to the power 20. That's a big number. Okay, that's a lot of zeros. And so it's highly shifted to that. So again, I wanted just to share that with you. So you can see that with the weaker base, I have an equilibrium, but with the stronger base, it goes all the way towards enolate formation. And again, I'm going to emphasize here that the base has to be in excess in this case, aldehyde. So to answer the question, why is this non-nucleophilic, is recognize that in the chapter of aldehydes and ketones, you should have learned how that aldehydes and ketones react with amines, depending if they're primary or secondary, they either make imines or enemies, right? And one of the things you should have learned from Dr. Schwann is that amines react with aldehydes and ketones specifically by the fact that the carbonyl is electrophilic at the carbon, and the nitrogen is a nucleophile, okay? So this nitrogen here, particularly since it has a negative charge, is very nucleophilic in principle. With nitrogen, with two sets of lone pair of electrons, should be very reactive, and that it should react at this carbon of this carbonyl. Well, it turns out these isopropyl groups, okay? So if you allow me to put down CH3 groups here, CH3 groups here, the van der Waals radii associated with all these carbons and protons around this basically block the lone pair of electron from attacking this electrophilic carbon. Okay, so that's why we say it's non-nucleophilic. However, it functions as a base because if I put a 2 here, and again, put a proton, protons are very small. This guy can attack this proton because it's significantly smaller than attacking this carbon. Also recognize that around this carbonyl, you have alkyl groups around it. So not only is this bulky, but the attack of this carbonyl here, because of these alkyl groups around it, also prohibit this guy in attacking in this direction. So I'm going to draw an arrow just to show that with you guys. And because this is basically sterically hindered, and this is also cumbered, this does not happen. Okay, so what I often tell students is aldehyde was specifically designed to be only a base by the fact that we want to minimize its ability to attack as a nucleophile to that carbonyl.
That makes more sense. Thank you.
Okay, so that's what we're really getting at. Is trying to maximize this happening and not that. Okay, because again, a proton is significantly smaller than this carbon that has these flanking methyl groups around it. So again, we minimize this attack by basically putting large isopropyl groups on each side of that nitrogen to hinder its attack as a nucleophile to the electrophilic carbonyl. Okay?
So does that mean you can basically use any bulky base like that? Or does it have to be LDA?
There are other bulky bases, but specifically here for our class, we're only going to use LDA. Okay, but there are chemists have played with the gamut of other synthetic hindered bases. So there is I've probably used 2 or 3 others in my career. So there are others, but again, specifically for our course, I just want you to recognize that LDA is it's a strong base. What does that mean? Well, it drives this equilibrium all the way to the right to enolate. And because it's hindered here, it only functions as a base and not as an nucleophile.
Okay, thank you.
All right.